Okay, well, the idea of this first video is to tell you what's coming, to give a kind of outline of what is reasonable to learn about ordinary differential equations. And a big part of the series will be videos on first-order equations and videos on second-order equations. Those are the ones you see most in applications, and those are the ones you can understand and solve when you're fortunate. So first-order equations means first derivatives come into the equation. So that's a nice equation that we will solve, we'll spend a lot of time on. The derivative that's the rate of change of y, the changes in the unknown y as time goes forward are partly from, depending on the solution itself. That's the idea of a differential equation, that it connects the changes with the function y as it is. And then you have inputs called q of t, which produce their own change. They go into the system, they become part of y, and they grow, decay, oscillate, whatever y of t does. So that is a linear equation with a right-hand side with an input, a forcing term. And here is a nonlinear equation. The derivative of y, the slope, depends on y, so it's a differential equation. But f of y could be y squared, or y cubed, or the sine of y, or the exponential of y. So it could be not linear. Linear means that we see y by itself. Here we won't. Well, we'll come pretty close to getting a solution because it's a first-order equation. And the most general first-order equation, the function would depend on t and y. The input would change with time. Here, the input depends only on the current value of y. I might think of y as money in a bank, growing, decaying, oscillating. Or I might think of y as a distance on a spring. Lots of applications coming. Okay, so those are first-order equations, and second-order have second derivatives. The second derivative is the acceleration. It tells you about the bending of the curve. If I have a graph, the first derivative, we know, gives the slope of the graph. Is it going up? Is it going down? Is it a maximum? The second derivative tells you the bending of the graph, how it goes away from a straight line. So, and that's acceleration. So Newton's law, the physics we all live with, would be acceleration is some force. And there is a force that depends, again, linearly, that's a key word, on y, just y to the first power. And here is a little bit more general equation. In Newton's law, the acceleration is multiplied by the mass, so this includes a physical constant here, the mass. Then there could be some damping. If I have motion, there may be friction slowing it down that depends on the first derivative, the velocity. And then there could be the same kind of force term that depends on y itself. And there could be some outside force, some person or machine that's creating movement, an external forcing term. So that's a big equation, and let me just say, at this point, we let things be nonlinear and we had a pretty good chance. If we get these to be nonlinear, the chance at second order has dropped. And the further we go, the more we need linearity and maybe even constant coefficients, m, b, and k. So that's really the problem that we can solve as we get good at it, is a linear equation, second order, let's say, with constant coefficients. That's pretty much pushing what we can hope to do explicitly and really understand the solution. Because, so linear with constant coefficients, that's, say it again, that's the good equations. And I think of solutions in two ways. If I have a really nice function, like an exponential. Exponentials are the great functions of differential equations. They're great functions in this series. You'll see them over and over. Exponentials, say f of t equal e to the t, or e to the omega t, or e to the I omega t. That I is the square root of minus 1. In those cases, we will get a similarly nice function for the solution. Those are the best. We get a function that we know, like exponentials, and we get solutions that we know. Second best are we get some function who we don't specially know. In that case, the solution probably involves an integral of f, or two integrals of f. We have a formula for it. That formula includes an integration that we would have to do, either look it up or do it numerically. And then, when we get to completely nonlinear functions, or we have varying coefficients, then we're going to go numerically. So really, the wide part of the subject ends up as numerical solutions, but you've got a whole bunch of videos coming that have nice functions and nice solutions. Okay, so that's first order and second order. Now there's more, because a system doesn't usually consist of just a single resistor, a single spring. In reality, we have many equations, and we need to deal with those. So y is now a vector, y1, y2 to n different unknowns, n different equations. That's n equations. So here, that is an n by n matrix. So it's first order, constant coefficients, so we'll be able to get somewhere, but it's a system of n coupled equations. And so is this one with the second derivative. Second derivative of the solution, but again, y1 to yn, and we have a matrix, usually a symmetric matrix there, we hope, multiplying y. So again, linear, constant coefficients, but several equations at once. And that will bring in the idea of eigenvalues and eigenvectors. Eigenvalues and eigenvectors is a key bit of linear algebra that makes these problems simple, because it turns this coupled problem into n uncoupled problems, n first-order equations that we can solve separately, or n second-order equations that we can solve separately. That's the goal with matrices, is to uncouple them. Okay, and then really the big reality of this subject is that solutions are found numerically and very efficiently. And there's a lot to learn about that. A lot to learn. And MATLAB is a first-class package that gives you numerical solutions with many options. One of the options, maybe the favorite, ODE for ordinary differential equations, 4, 5. And those numbers 4, 5, well, Cleve Moeller, who first wrote the package MATLAB, is going to create a system of a series of parallel videos explaining the steps toward numerical solution. Those steps begin with a very simple method. Maybe I'll put the creator's name down, Euler. So you can know that because Euler was centuries ago, he didn't have a computer, but he had a simple way of approximating. So Euler might be ODE 1. And now we've left Euler behind. Euler is fine, but not sufficiently accurate. ODE 4, 5, that 4 and 5 indicate a much higher accuracy, much more flexibility in that package. So starting with Euler, Cleve Moeller will explain several steps that reach a really workhorse package. So that's a parallel series where you'll see the codes. This will be a chalk and blackboard series where I'll find solutions in exponential form. And if I can, I would like to conclude the series by reaching partial differential equations. So I'll just write some partial differential equations here so you know what they mean, and that's a goal which I hope to reach. So one partial differential equation would be du dt. You see partial derivatives is second derivative. So I have two variables now, time, which I always have, and here is x in the space direction. That's called the heat equation. That's a very important constant coefficient partial differential equation. So PDE as distinct from ODE. And so I write down one more. The second derivative of u is the same right-hand side, second derivative in the x direction. That would be called the wave equation. So this is like the first order equation in time. It's like a big system. In fact, it's like an infinite sized system of equations, but first order in time or second order in time, heat equation, wave equation. And I would like to also include the Laplace equation. Well, if we get there. So those are goals for the end of the series that go beyond some courses in ODEs, but the main goal here is to give you the standard clear picture of the basic differential equations that we can solve and understand. Well, I hope it goes well. Thanks.